Hi everyone, and welcome to part 2 of kernels and processes 2. Here we're going to be looking at Unix and process management. Okay, so what is Unix? Well, Unix is a family of multitasking, multi-user computer operating systems that derive from the original AT&T Unix. So it's like a collection of operating systems like welded together in different ways and stuff like that to perform different tasks. So a lot of different people have added different components to it, and it has formed the foundation of like Linux as well as Mac OS. Now we'll be looking at a subset of the programming interface of Unix. Specifically, we're going to be looking at two components, and that is process management and input-output control, like a brief introduction to input-output control. So process management. So traditionally, in the early days batch processing systems, so the early days of batch processing systems, the kernel handled process management by necessity. There was no other way of doing it. But some time went by and a different approach was developed. And that was one that allowed user programs to create and manage their own processes. So web browsers for managing embedded scripts, and like Windows or window managers managing various windows, for example. Now, an early motivation for user-level process management was to allow developers to write their own shell command line interpreters. Now, like I said, you might have heard this phrase shell before, but it is actually just as simple as a job control system or a job management system. Now, Windows and Unix both have a shell, and the reason for this is that, well, many tasks involve a sequence of steps, right? Now, each of which could be their own program. And with a shell, you can write down these sequences or these sequence of steps as a sequence of programs to run. For example, makefiles are a form of a shell or a type of shell or an example of a shell that is utilized to compile multiple C programs, right? When you design your makefile, it will have a sequence of lines indicating which file to build or which file to compile, and this is a sequence of steps, right? Now the C compiler itself is also a shell program. The compiler first invokes a process to expand like the header and include files. It then it has separate processes that passes the output, a separate process that passes the output. Another process to convert to assembly, and lastly a process to convert that assembly into like machine executable instructions or executable machine instructions. So you can see quite a few things are shells or shell programs. Now, we've talked about this a little bit already last week, but how does Windows handle process management? Well, Windows simply has system calls to handle process operations. For example, like we spoke about last week, there's a specific system call to handle the creation of processes. This was the create process. Now, in terms of Windows specifically, the idea here is that their process management system calls are simple in theory and simple to understand, but complex in practice. Okay, and I'm not going to go into too much detail about it, but because we talked about this last week in terms of the process API. But let's just rehash it a little bit. So what steps does create process take? Well, it creates and initializes a PCB in the kernel for this specific process. It creates and initializes a new address space, so a space for this process to exist. It loads the program into the address space. It copies the arguments into the memory in the address space. It initializes the hardware context to start execution at the start of the program. So what do we mean here? Hardware context to start execution. So this is basically, it's updating the program counter to point to the start of the program. Why? Because, well, the program counter stores the instruction that is going to be processed next. So if you want to start a program at the start of the program, well, change it so that the program counter is pointing to the start of the program. And lastly, it informs the scheduler that a new process is ready. Now, Unix handles things a little differently. So Unix is complex in theory, but simple in practice. So Unix splits create process into two steps called fork and exec. So here we have an example of some code that demonstrates this functionality or this timeline. So we have PID equal to fork, then if PID is equal to 0, exec else wait. Okay. So this fork command basically creates two processes that are identical. So let's speak about just the fork component firstly. Okay, so what does Unix fork actually do? Well, like I said, it creates a complete copy of the parent process. The only difference is the ID which is used to identify it. And for the child process, it is set up with the same privileges, priorities, and input-output the parent would have. Now, the PID is basically a process ID, so it's an identifier that indicates which process this is, and it is a unique identifier. Now, what are the steps that Unix takes? What is the steps does Unix fork take? Now, it's similar to obviously the Windows approach, but slightly different. So as in Windows, it creates and initializes the PCB and the kernel. It creates a new address space, and it initializes the address space with a copy of the entire contents of the address space of the parent, as well as any inherent execution context of that parent. So this means, well, if the parent had opened a file during its processing or during its execution, well, then this file needs to have been opened for the child as well. And lastly, it informs the scheduler that the new process is ready to run. Now, what is strange with the Unix fork is that the system call returns twice, once for the parent and once for the child. Now, the parent receives the process ID of the child, and the child receives a 0, indicating that it was successfully created. Now, like I alluded to before, well, there's these other two components, the exec and the wait. So what is Unix exec? Well, once the context is set up, the child process calls the Unix exec command, and this brings the new executable image into memory and runs it. It then takes in as parameters the name of the program and the arguments for it. Okay? So this is basically actually executes that process that you've now created. What steps does Unix exec take? Well, loads the program into specified into the current address space, copies the arguments into the memory and the address space, initializes the hardware context to start the execution at the start. And by hardware context, once again, we mean the program counter. And then we have Unix wait. So often parent processes need to pause for child processes to finish or to do something. And for this we use wait. Now it pauses the parent process until the child process is finished being executed. And to do this, Unix wait takes in the process ID for which the parent must wait for. So if the PID is 3, well then it will wait for, say, the process 3 to finish. Lastly, we have Unix signal, and this is going back to those upcalls that we were talking about. Now, Unix signal or Unix provides a facility for one process to send another an instant notification. Now, you remember when we were talking about uses for upcalls, there was that inter-process communication. Well, this is it in action. Now, this notification, or this instant notification, is sent using Signal. So those are the various commands or functions that Unix utilizes to handle its process management. Now, the last thing we're going to be looking at today is input and output. So computer systems have a wide variety of input-output devices, right? You got a wide variety of keyboards, mice, Ethernet, display, cameras, printers, a lot of different things, right? Now, to deal with this diversity, we could specialize in the application programming interface for each device, right? We could come up with a solution for each individual device, customizing it to the device's specific characteristics. But if you remember back all the way to the beginning, this goes against the whole design ethos of operating systems, where it's generalizability, and it's an abstraction away from specific hardware components or specific characteristics of hardware. But for an example, a disk is obviously quite different from a network, though. So data on disks are addressed in fixed sizes, whereas a network sends and receives streams of variable sized packets. So for this specific example, you can see there is an inherent approach at designing these solutions to be super specific, because you'll just have to design so many, right? And in terms of what is the inherent problem to this approach, well, that is it. The problem here lies in the fact that every time a new hardware device is invented, the system call interface has to be upgraded to handle this change. So we'd have to keep updating our operating systems over and over again for every specific new version of a hardware device that is released. Or if a hardware device is updated even, then we would have to update that system call interface as well. So one of the primary innovations of Unix was to regularize all the input and output behind a single interface. And unknowingly, you have seen this interface in use before. Now, Unix even uses the same interface for reading and writing. And that this approach was so successful that it's almost universally followed today. And the terms that you're going to see now are going to give it away. Now, the basics ideas behind this Unix I/O was that all device input-output, file operations, inter-process communication even, should use the same set of system calls. And these were open, close, read, and write. So whenever you've opened a file, closed the file, read or written lines, you've utilized these lines, right? Or these instructions. And these are utilized for everything in terms of file operations, input, output, inter-process communication, all of them. Didn't matter which hardware, which specific input-output device you were reading or writing from, you would always use these same commands. And that was one of the basic ideas of utilizing uniformity. Another was open before use. Now, before an application does any input or output, it must first call open on the device, file, or communication channel. And this gives the operating system time to check permissions and record logs, so they can check, well, is this a valid argument or not? Another idea was that they made it byte orientated. So all devices, even those that transfer fixed size blocks of data, are accessed with byte arrays. And communication is also handled using bytes. So instead of, say, this device being handled using lines, like if you're reading from text files and you would read lines in, everything is handled at this level in a byte-orientated fashion. Obviously, when you get higher up, maybe in your actual program, then you could change it so that you're reading line by line, but behind the scenes, you're reading byte by byte. And another idea here was that they wanted kernel buffered reads. So stream data such as from like a network are stored in these kernel buffers and are then returned to the application on request. So the data gets streamed basically into like kernel memory in this kernel buffer, and then on request it gets provided to the application program. And just with reading, they did the same approach to writing. So outgoing data is stored in the kernel buffer for transmission when the receiving device becomes available. And just like we had explicit open, well, we have like an explicit close. So when an application is done with a device or file, it calls a close command. And this signals to the OS that it can decrement the reference count on the device and garbage collect any unused kernel data structures. So any of that buffered information it can just remove. So what does this actually look like? So how does Unix handle this I/O? So Unix implements what they call pipes. Now a Unix pipe is a kernel buffer with two file descriptors. A file descriptor just describes the file. It has metadata regarding that file. And it has one for writing, so putting data into a pipe, and one for reading, which is pulling data out of the pipe. So you'll have a producer who writes data, and this gets piped into that kernel buffer, right? And then on request, it can get read by the consumer. And because we've decoupled this execution of the producer and the consumer, we get the benefit of reducing waiting time between processes, okay? And the internet itself, in terms of TCP, works in a similar way as Unix pipes. So when a consumer requests information, it doesn't then tell the producer to write. The producer could have written it way before and then requested. So we don't have to wait for this communication between consumer and producer. The consumer can just read whenever it wants to from the pipe, and the producer can write whenever it wants to the pipe. Now, lastly, Unix utilizes a handle to be used in later calls of read, write, and close to identify the file, device, or channel. So I spoke about this before, but this handle is basically called a file descriptor. And by default, these are set to the terminal. So for example, I know I haven't really made this clear, but it identifies which device or channel that information should go to. And by default, this is the terminal. So for example, I will read information from the terminal into a read buffer, and I will write information to the terminal from the write buffer. Obviously, if you're saving stuff to like a text file, your file descriptor will be changed, or it will have been changed so that it's not set to the terminal. It will be set to like an output file. But it is this file descriptor that determines or handles where these streams of data come from and go to. Now this is just a little bit of fluff on top, but how do we set these file descriptors? Well, within a program you can actually utilize a special command called DUP2, and it takes in an input from and two inputs from and to, which can change the file descriptors of a process. For example, I can change my keyboard's file descriptor to write to a file instead of the terminal or screen. So by default, when I press L or P, it's writing to the screen. This is L or P on like the keyboard. But I can manipulate the file descriptor using this DUP2 command so that now it just automatically writes to like a specific file. So that's quite cool and interesting. But that is essentially how Unix handles process management, as well as how Unix handles input and output. Now that is it for this week's lecture. If you guys have any questions regarding it, I know it's quite a bit of theory so far, but I thinking I'll do like a summary lecture, which will just have all the key points from all the topics we've discussed, as the last thing when I'm referring to virtualization. So that will come out in maybe the next couple of weeks. So thank you once again, and if you have any questions, feel free to post them on Moodle. Otherwise, enjoy your week.